All right, so hello again. We're going to do chapter 26 homework problems that were turned in. Those are problems 3, 5, 6, 7, and 8. And I'll be answering them up here on this board. And so you can watch the ones that you need, or you can watch all of this video. I do want to remind you that for class next week on Thursday, we will be covering the next chapters. So you should be working on the I think it's week 5, and then week 6 is a signature assignment and the final, which will give you a little bit more time after their November 7th last class date. So we'll talk about that next week as well. I did open all of the week, so you can work ahead if you like, and everyone should have been working on the signature assignment since the first week, so we want to make sure that we're compiling all of those activities and the PDFs onto our online portfolio. So let's get started and look at the homework problems. I pre-drew these figures for the problems at the end, but we're going to start on number 3. And number 3 is about Pythagorean triples. We didn't get to do some work on Pythagorean theorem last time. We had so many chapters to cover with geometry. But the Pythagorean theorem is a really important theorem in mathematics. It is related to just one type of triangle, the right triangle. And there's a lot of patterns and theorems and proofs that we can get into. Really take a whole class period just doing that. But we'll look at it a little bit maybe on this last week. But Pythagorean triples are when you have 3 numbers that work exactly perfectly into Pythagorean theorem. And so the example that was given in the book, or one of the examples, is your 3, 4, and 5. So this is what it means. The Pythagorean theorem says that a squared plus b squared equals c squared. That's a formula that we always memorize. But what that means in a Pythagorean theorem, or Pythagorean triple, is that 3 squared plus 4 squared exactly equals 5 squared. That doesn't happen with all numbers. But for the numbers where it works, like 3, 4, and 5, then we call those Pythagorean triples. There's several Pythagorean triples. Some of them are in the problem that are listed as examples. And then you're given a list. You're given a list of possible Pythagorean triples, and you're told to figure out if they are or if they're not. So for example, one that was given to you was 9, 12, and 15. So what you want to do is you want to go to your Pythagorean theorem, which is this formula, and you want to put just each of those numbers down and see if they work. So does 9 squared, which means 9 times 9, if you get that answer and add it to 12 squared, which is 12 times 12, do you get, question mark, would mean, does it equal 15 squared? 15 times 15. So 9 times 9 is 81. And 12 times 12 is 144. The question is, does it equal, I think this is 225? And if it does, then you put yes, that's a Pythagorean triple. If it doesn't exactly give you this number squared, it's a little bit off, then it's not a Pythagorean triple. So it has to be an exact whole number, no decimals, exactly equal to that number. So that's a yes or no answer. And in this case, it is a yes. So that is our Pythagorean triple. The other questions that are on that same problem are about factors. So let me erase this and we'll get into a little bit of what it means when they say factor. So for example, it says factor of 7. Can you find some Pythagorean triples that are factors of 7? So we want to go back to what that means, factor of 7. Maybe it would have been a little bit more clear if it said multiples of 7. Because if we look at the number 7, we can think about multiples of 7. So we can count by 7s. That's what it means. So 7, 14, 21, 28, I wrote 35, 42, and 49. And the list can go on. The Pythagorean triples should be close to this list. It shouldn't be something that's way out. I didn't look at all of them, but you want to look at any factors of that number, which means any multiples of that number. So we're trying to figure out, is there a set here that equal a Pythagorean triple. So you would have to test it out. You may start in any place you want, but for example, does 7 squared plus 14 squared equal 21 squared? And I'm going to put a question mark over the equal sign because I don't know if that equals. Now, if this does equal, these two things added together, squared and added together equals 21 squared, then it is a Pythagorean triple. If it's not, then shift over to the next three numbers. Try 14, 21, and 28, right? If not, try a next set. Or you can skip around and try it as you wish, but they should be consecutive when it says, is it a factor of 7 that has the Pythagorean triple? And that's what it's kind of coming out to. There's a lot of different ones that are given to you there, but I wanted to use this as an example of what that means when it says a factor of. All right. So let's go on to number 5. And in number 5, we switch over back to the idea of proportions. But in this case, looking at a ratio that's actually a rate. And rates are a very common way we see ratios in everyday life. So how fast we go, miles per hour, that's a rate. When we go to the store, so many ounces cost this much money. So that's a unit rate. And in this case, we're told that, I think it's a speed, so 100 meters in 10 seconds. So we're given a speed. So again, this is number 5. And we are given a speed of 100 meters in 10 seconds. Right, so every 10 seconds, this is how far it goes. And a speed is that relationship between both of these. And we're asked to find out the unit rate, really. We're asked to find out how fast is this speed in 1 second. So in 1 second, how far do we go? So one way you can figure that out is to think about it as a proportion, as two ratios that are equal to each other. So we know one of our ratios can be 100 meters per 10 seconds, right? And you can write seconds and meters over each other, but this is the way we're commonly seen, right? It's commonly seen. So miles per hour. So we usually have the distance per the time. And we want to figure out how far, so that's blank, in 1 second, right? So again, we go back to what we just did in chapter 20 was with proportions, and how we can solve a proportion is cross multiplying and dividing. Now, maybe you already recognize that that was going to be true here, and you would have already divided that. You can see that that is true, that 100 meters divided by seconds will give you that unit. If you already knew that, that's fine. You don't have to solve it through the proportional way, but this is just justifying that kind of thinking process. So 100 times 1 is still 100, and then you take your 100 and you divide by 10, and you would get how fast you would go in 1 second. To continue on in this problem is then to go a little bit deeper and to think about the units that we use. So in this case, we're doing meters and seconds and seconds. This works because all of our units are consistent. But in the next problem, there is no consistency. So we're given the same type of problem, but we're extending it. So down here, I'm going to write what it asks. It asks us to find if we still have this truth about the speed that we're going. Well, then how many kilometers per hour are we going? Okay, so per hour would tell us in 1 hour. So now we still have a proportion and we still can solve it, but we have to be conscious that our units are not identical. And because they're not identical, we first have to fix that issue before we can solve the problem. So we have to change 100 meters into a kilometer reading, and then we have to change our seconds into hours. Now, this is a little bit more difficult than when we're going from something that's larger to smaller, because what we're going to have here is decimals. These are parts of a whole, because we know that Seconds compared to hours, seconds is a lot smaller. And the same is true for meters and kilometers. So that is an issue that you have to deal with, but that's okay because you have to think about a proportion as being any unit that you can use. So that's okay if these are decimals. It'll still be solvable. We can still solve this. So to do that, we have to think about first, how many meters are in a kilometer? Well, there's 1,000 meters in 1 kilometer. Well, if it takes 1,000 meters to make 1 kilometer, then what fractional part of meters do I have? And to solve that, you would just take your 100 divided by your 1,000, okay? 100 meters is what you have, and 1,000 is what you need to make 1. So that would give you the proportion that you need. And that turns out to be 0.1. So I'm going to change this here into my kilometers unit, but I'm not changing the value. I'm just changing how I'm writing it. So 0.1 kilometers equals that 100 meters. And I got that from 100 divided by 1,000. All right, now I have to change seconds into hours. What part of an hour is 10 seconds, right? So the question is, how many seconds are there in an hour? Because then I know the whole and I can compare it to the part that I have. The part that I have is 10 seconds. The whole, I have to figure that out. So in 1 hour, we have 60 minutes. And in every one of those minutes, we have 60 seconds. So we have 60 60s. So you have to multiply 60 times 60, and then that will give you the whole that we have, right? So think about that first. And then when we have that piece, we can then continue to figure out the part that we have the whole, right? So I know that 10, and I'm going to divide it into the whole. So whatever 60 times 60 is, I'm going to do 10 divided by that answer. 10 divided by 60 times 60, right? And I already figured that out here, so just cutting to that really quickly. That turns out to be a decimal answer that's pretty long. I'm going to write an approximate and then know that when I get my answer, I'm going to have to round up a little bit. So it's 0.00277, and then it kind of continues, and then it rounds the last digit to 8. All right. So this is in hours. That's 10 seconds converted into hours, right? So then what you want to do is you want to think about 0.1 times 1, which is the same answer, and then 0.1 divided by this number, which is, looks like a long number, but it's actually really small because it's a decimal answer. And what you're going to get is 35.999 or something close to that. So just round that up to 36 because we had approximate here. And so that's going to be your 36 kilometers, right? So that's how fast the speed is in kilometers per hour. Make sure you know how to do this. Make sure you know how to convert. If you have any questions about that, bring those questions next week. But this is an important piece of mathematics that's really important in science and mathematics and medicine, converting to different rates and to different units. All right, so now let's look at number 6. And number 6 is corresponds to one of the drawings I have up here. I'm going to go ahead and erase this out. And I'm going to move the camera just slightly. I know there's a little bit of a glare, hoping that you can still see that accurately. We have that prism box drawn here, the same one that you have in your book and on the screen. And I've just put in the information that was given, which is the 8 is the height of this box, 5 is the width of this box, and 12 is the length of this box. And it's hard to see on this drawing, but there's a dotted line that goes from this corner down to this corner. And it's actually going across the box. So if you were looking across that box, it would be like if you imagine a yarn that's going from this top to that bottom that's closest to you, then you would be able to see that, right? So in this case, we have to think of it in right triangles because right triangles are a great tool because we know we can use the Pythagorean theorem to find missing sides, right? So we're going to assume that this box is a rectangular prism. That means that the angles of it are in 90 degrees, and we're going to be able to solve the missing sides that we have. And in this case, it's going to be 2 steps to be able to do that. So I see that the triangle that I have to find is almost like a triangle that's cut out and cutting that rectangular prism in half almost. It's using this height of 8. This dotted line right here is the hypotenuse, and then a line that goes from there across the base to this corner would be the other leg. Now, in the Pythagorean theorem, I need 2 sides at least to find the missing third. And right now, what I have isn't enough information. So what I need to find first is this line that goes across the base. I can find that because I know the 5 and the 12. So the first problem that you want to solve is this 5 squared plus 12 squared equals something squared, right? And that something would be what I need to do my next problem where I can actually solve for the answer I'm given. So remember that when you take these 2 numbers and you multiply them by themselves, and then you add them together, you're going to get this missing side. We can call it c squared if we want to, because we know that that's in the formula, so that might help you. And actually you get 169, which turns out to be a Pythagorean triple that we can use here, or 3 numbers that work out perfectly, because 13 is the exact square root of 169, and that's what c equals. Remember that in algebra you always do inverse operations, and the inverse of a square is a square root, and that's what we're doing. We're taking the square root on both sides to figure out what that is. So when this turns out to be 13, now I have 2 sides and I can find the missing side. And the missing side in this case is that dotted line that I'm given. So you're going to then apply this information to write a new problem. The second problem would be your 8 squared plus 13 squared, which is what I just found. And your c squared is the answer that you want to have in order to solve this problem, right? So solving that would give you that dotted line. Now remember this, that a lot of mathematical problems we're solving aren't easy to solve, right? And so we have to think in steps and applying and getting the information we need to solve the problem that we're given, right? Misunderstanding, misconceptions with students is to solve a problem and say I'm done because I have an answer, right? And not to think through, is this the answer though that answers the question I was targeting? This is part of the answer, but I'm not done yet, right? And to keep on going and then to solve for what they need, all right? So I'll let you finish that one up in number 6. All right, so let's look at number 7. Number 7 isn't really a problem. It's more of a concept that I want to clarify and make sure that you understand, all right? So the exponent 2 is called a square, right? It's a times a. So when we say this formula, we say a squared plus b squared equals c squared. We also have to realize is that there's a shape called square, and the area of a square is its side times its side, which is the side squared. So one of the proofs of a Pythagorean theorem is looking at a right triangle and looking at the sides. And the 2 legs here, you always have a smaller and a larger. If we extend those and use them to duplicate and make a perfect square, then each of these are the exact same length, and then we have an area, right? And we could do the same thing over here, and I'll try to draw it as best as I can, that we have an area here, right? Those 2 areas, when we combine them, when we add them together, we will have we will have an area that is equal to a square that we can make right here. Okay, and those two areas combined will be that area. Okay, that's one of the proofs of Pythagorean theorem. I'm not sure how many different proofs there are. I know there's dozens of proofs of Pythagorean theorem, but this is a concept that has to do with actual area, and is one of the ways to think about the Pythagorean theorem. So it's a good founding for you to understand it a little bit more, and it's a good way to explain visually what it means. Right? So let's go to our last problem, and our last problem is number 8. And we're given a right triangle, and we're given some of the information of the triangle, and we have to find the missing side. And in this case, we're given that our x is 5, so I'll just write 5 up here, and that our z is 10. And we don't know what this part is. Now, in the Pythagorean theorem, a lot of times we're looking for the hypotenuse, but not all the time. Sometimes we're looking for one of the missing legs, and that's what's happening here. So we want to make sure that we fill this out with the formula correctly, right? And it will look something like this. You still do the same thing. You're still going to square the numbers. And what you have to remember is now that you have your variable in the center, you need to isolate it. And to isolate it, we'll need to subtract this number over here to this side, okay? So minus 25 and minus 25 will give you y equals 75, and that's a y squared. So we have to inverse that operation to figure out what that is. So you're going to take your calculator, put 75 in there, and hit the square root button, and you're going to get an approximate. And that's where the answers are saying between this number and this one, because we're approximating what that is. Can't get the exact answer because 75 doesn't have an exact square root. So that's how we solve ones that we're just trying to find the leg of the triangle. All right, so I hope those problems that you asked for, your homework problems, help you finishing up your homework. Make sure that's turned in, of course, by Saturday, and that I believe we extended the midterm until Monday. So make sure you have your midterm done on Monday. Again, if you have any questions, and if it's something you need a quick feedback on, make sure you use aileen@aimcenter.org as my email. And then otherwise, I've graded week 3. I'll work on grading week 4, making sure everything is there. If you have any questions about your grades, please send me an email, and I will see you on Thursday at the North Center at 6 o'clock for our last class. Thank you for all your hard work, and I hope you have a great weekend.